So we will simplicial. Before we discuss simplicial homology, we need to discuss simplicial complexes. Simplicial complexes. So definition. So we will discuss actually a number of definitions. A set V naught, V1 and so on, Vk uh, in Rn with n less than equal to k less than equal to k less than equal to n is I said this in Rn is said to be affinely or linearly independent. Affinely linearly independent or in general position. If this set V1 minus V naught, V2 minus V naught, and so on, Vk minus V naught. This is linearly independent. In Rn. So of course we will see some definition, some examples of affinely linearly independent subsets. So for example, if you are in R2, right, then if you just take two vectors, so suppose you are so this V0, V1, V2, and so on, Vk, they are actually vectors. They are so we can treat them as vectors. Also, we can treat them as points, right? So if this is origin, right? So if we want to treat, suppose this is your V0, right? So if you want to treat this as vector, then this will be the vector, right? And if this is V1, then if we want to treat V1 as vector, then this will be vector. Otherwise, if we want to treat V1 as point, then this will be the point. Now, so is this question, is this set V0, V1, is this affinely linearly independent in R2, right? So for that, what we have to do, we have to just find out if V1 minus V0, right, is linearly independent. This is linearly independent if and only if V1 minus V0 is non-zero. It is a non-zero. Uh, so so basically this V1 minus V naught in this case is independent. Now, what if we take 3 points in R2? Suppose we take V0, V1, V2, V2. Yeah. So we have this, right? So V2 minus V0, it is this vector, and V1 minus V0 is this vector, right? So question is, are these two vectors linearly independent? Yes, we can verify that they are linearly independent. Basically, they are not collinear, so they are linearly independent. So these 3 points V0, V1, and V2, they are in general position, right? Are these vectors V0, V1, and V2? They are affinely linearly independent. Now, if I take another point, right? Suppose V3 here, right? So no. So what we can do? So these are in general position. Now, if we take a vector V2, which is here, right? Then V2 minus V0 is this vector, and V1 minus V0 is this vector. So this vector and this vector, they are they are not linearly independent, and hence these V0, V1, V2, these 3 points, they are not in general position, or they are not the vectors V0, V1, and V2. They are not affinely linearly independent vectors. So similarly, in R3 also we can talk, right? Next definition is let V0, V1, and Vk be an affinely linearly independent set of k plus 1 points in Rn. Right. The simplex So its plural will be simplicious, right? So plural, if we have more than one simplex, then we will call them simplicious. Plural will be uh, simplicious. Okay. Uh, so the simplex is spanned by V0, V1, and so on, Vk, and denoted by V naught K is simple. It is the set. Is the set. This summation Ti Vi I equal to 0 K such that each Ti is greater than equal to 0 and summation Ti is 1. With subspace topology. So this is a subset of Rn, right? So if you induce the topology from Rn over this set, then whatever you get, that is called a simplex, right? So this set with induced topology, right, uh, from Rn, it's called a simplex. So what? Suppose you are in suppose you are in R1, right? Then if you choose a point V0 here, another point V1 here, then of course V0 and V1 will be in general position, right? Now simplex. So what is this? What is this V0 V1 in this case? So if you see, then this is going to be actually this interval, simply this interval, this closed interval, because you have this summation Ti I equal to 0 to 1 Vi. Okay, this is what, and summation Ti equal to 1. So this you can write as T naught V naught plus T1 V1, right? But this you can write as T naught V naught plus 1 minus T naught V1. So this is a line segment joining V naught and V1. T naught is greater than equal to 0 and less than equal to 1, of course, from here. Because this condition is there, so each T naught will have to be less than equal to 1, because each T naught is greater than equal to 0. Now, so this is a simplex spanned by V0 and V1. Now, now if we are in now if we are in R2, suppose V0, V1, V2. Right? Then you can verify that the simplex, so these 3 points, they will be in general position. So we can verify that simplex spanned by this is nothing but this triangle, whose vertices are these V0, V1 and V2. So this we can verify. Because if we put T naught equal to 0, right? So this is basically your simplex spanned by V naught, V1 and V2 is what? It is the collection of the points T naught V naught plus T1 V1 plus T2 V2, where T naught Ti is greater than equal to 0 and summation Ti is 1. Now if you put T naught equal to 0, then what you will get? You will get basically this vertex. This means is bar boundary, you can see. If you put T2 equal to 0, then you will get this. If you would put a T1 equal to 0, then you will get this, right? In other cases, you will get points inside. So that you can verify. Okay. Next, uh, next, what we can see what is actually this uh, simplex spanned by 4 points in R3. Suppose we are in R3, and again if we take 3 points, then 3 points which are in general position, right? Then the simplex is spanned by the 3 points will be again our triangular disk, you can say. Okay. Now, if we take 4 points in R3 which are in general position, then we can verify that. So if we take like this, then so this is V0, V1, V3. Now, this will give this. This, right? And then so this we are getting into tetrahedron. Okay, so we are getting tetrahedron with 4 faces, 4 vertices, right? And this is actually the simplex spanned by V0, V1 and V0, V1, V2 and V3. Next, for if we have a simplex, then for any point if we choose a point X, of course, it will be given by this in a simplex spanned by V0, V1 and Vk, right? Then the numbers Ti are called the barycentric coordinates of X. The barycentric coordinates of X with respect to each of the points uh, here, each of the points vi is called each of the points vi is called a vertex. Each of the points vi is called a vertex of the simplex. Simplex, this V naught, this and this K is called the dimension of the simplex. A k-dimensional simplex is often called a k-simplex. K-simplex. Let sigma v naught vk then each simplex is spanned by a non each simplex is spanned by a non-empty subset of the vertices of sigma is called a face. So one thing you should notice that if we have a set in Rn which is affinely linearly independent, then every subset of this will also be affinely linearly independent. So this you can verify. So this is affinely linearly independent means what? If and only if this set V I minus V naught I equal to 1 to k is linearly independent. Okay, this is equivalent to this Vi minus Vj, I equal to 0 to k, this is Vi minus Vj, such that I equal to 0 to and so on k, I is not equal to G. Okay. This set is linearly independent. So if you can show this one, this and this, these two are equivalent, then you can conclude that this uh, every subset of an affinely linearly independent set is affinely linearly independent by using the fact that every subset of a linearly independent set is linearly independent. So what before that you need to show this. Next, uh, so the k minus 1 dimensional faces of a k simplex are called its boundary faces, are called its boundary faces. We define the boundary of sigma to be the union of its boundary faces. So if we take one simplex, right, then its boundary faces are what? This vertex and then this vertex here. And its boundary includes these two. Now if we take this simplex V0, E1, V2, then its boundary faces, this is two-dimensional simplex, two simplex, so its boundary faces will be its uh, one-dimensional faces, right? Its boundary faces will be actually its one-dimensional faces. So its one-dimensional faces are this one, and this one, and their union will be this. So this is the boundary of this simplex, two simplex. Now, if we take a three-dimensional simplex, right? So we will get a tetrahedron, and its boundary faces will be the triangular faces, which are two-dimensional. Two-dimensional uh, uh, faces, right, uh, of the three-dimensional simplex are actually boundary faces, and if we take union, then we will get boundary.